So we're on page 7 of the notes, 6.2. Before we start with the ugly notation at the top of the page, I just want to ask you if any of you know how to find the volume of something in 3 dimensions. Anything. Like the volume of a box or a sphere or anything that you might know. Yes?
Length times height times width, or like a cube.
Okay, or if it's a cube, even if it's not a cube, it could just be any rectangular solid. Look at me drawing in 3D. It doesn't happen very often and I'm not very good at it. Right, some 3-dimensional solid. It has some length, some width, and some height. So it could be a cube, in which case all sides would be the same, but the volume of this is the length times the width times the height. Most of you have seen that somewhere before in your geometry days or something. Anybody know how to find the volume of anything else in 3 dimensions? We're moving to 3 dimensions today. How about a cylinder? Even if you're guessing, I'll take guesses. I don't care if you're wrong. The volume of a cylinder that has some height and some radius, maybe? Yes?
Isn't something like 2 pi r times h?
Ooh, you're
Or 2
close.
pi r squared.
You're really close with the 2 pi r(h). He's close. Anybody know a slight tweak to what he said?
Is it pi r square h?
Pi r squared h. And I'm glad that you weren't 100% sure, because this is the point I'm trying to make. It's pi r squared h. And this guy, he was guessing. I liked your guess. I appreciate that. What is the area of the base of this rectangular solid? Just the base, the thing on the bottom.
Length times width.
Length times width. So that you have the area of the bottom times the height. Right? What's the area of the circle on the bottom of this, if I could actually draw? Pi r squared is the area of the circle times the height. In general, in 3 dimensions, if something goes straight up, it's the area of the base times the height. That's the volume. That's not area of the base. That's not look worse. It's not multiplication. I better put the word of in there. Otherwise you're going to say, what did she mean by that? Area of the base. There we go, times the height. So even if I had something that was, I can't draw this, like a triangle on the bottom, and then it went straight up, right? Oh dear. Pretend I can draw. That would be the area of the triangle times the height. Whatever's on the bottom times the height. If it goes straight up. And that's the whole point of what we're doing with solids of revolution. So the very first formula you see on the top of your notes there has this. Let's talk our way through it now that we mentioned that. It has the volume equals the limit as n approaches infinity. The sum of, we're using I, equals 1 to n. A of x I star delta x. That looks seriously scary. Seriously scary. It cleans it up a little bit and writes it this way, which is less scary, but we still don't know where it came from. So the whole point is that this is the, think of this part here as the area of the base times the height. This is the height. And what they're really doing is they're looking at things sideways. So imagine if I take, I don't know, what do I have here that I could use? Maybe this stack of papers right here. This stack of papers right here. If I could hold it flat. What's the area of the base? Length times width, so probably 8.5 times 11, right? Probably. And then the height is however thick this is. Maybe it's ½ an inch. So this is the area of the base they're talking about, and the height would be maybe ½ inch. The difference is they're kind of looking at it sideways. I remember yesterday or Tuesday we were talking about turning our head sideways. So the area of the base is actually a cross-sectional area. So if you look at the cross this side, it's the cross-sectional area. That's the area. And then the delta x is how thick it is. Remember the strip that had a little thickness last time? How thick it was for the rectangle? So that delta x is how thick it is. So you want to think of this as the I don't even know if this is a word, thickness. The thickness, I think thickness is a word. The thickness, how thick it is. The area times how thick it is. I observed another instructor teaching last semester, and she used an example of a loaf of bread. And it's all been pre-sliced so you can make sandwiches. But each piece of bread, oh, here I go trying to draw again. Someday I'll tell you about 2nd grade or 7th grade art. It was all bad. It was all bad. Loaf of bread kind of looks like that, and then it has a little bit of dimension to it, right? Because it has a little thickness to it. Piece of bread. Aren't you amazed by my art skills? But whatever this area is, we can figure out that, if you can figure out that area, I can't figure it out by that shape, but we can find that area times how thick it is would be the volume of that slice of bread. So any shape that you have, you take the area times how thick it is to get the volume. That's a big picture of what we need for everything we're doing today and next time, actually. Okay, so let's talk about solids of revolution. Oh wait, I didn't finish this. Who knows the relationship between this messy expression on the left and the messy one on the right, and the not so messy one on the right? What's the relationship between those? Go ahead, what are you saying?
Aren't they both sums?
They're both sums. If you didn't have this limit here, this says I'm adding, that's what that notation is, I'm adding about n rectangles or n shapes that are all some area times some thickness. I'm adding up a bunch of slices of bread maybe, right? And then once you take the limit, that means you're doing an infinite number of them and they're getting skinnier, and that's where the integral notation came in. So it's actually similar to what we did last time with the areas. Infinite number of rectangles to get area, now it's an infinite number of slices. So this means I'm taking the area times its thickness, same thing. Let's kind of work through a specific example, see if it makes more sense. Okay, solids of revolution. Example 1. Example 1 says to sketch this region and draw a representative rectangle. And then we're going to keep going with what it says. So it starts off similar to what we did on Tuesday. Let me write down my equations here. I have y equals x squared plus 1, x equals negative 1, x equals positive 1, and y equals 0. And we're going to improve our graphing skills here. What's that, a graph of? Parabola, where is it? Moved up 1? Beautiful. So maybe it's up here at 1. It looks something like this. Where this is 1 right here. There's my parabola. X equals negative 1.
Vertical line.
Vertical line over here at negative 1. So here's x equals negative 1. And another one over here at x equals positive 1. And where's y equals 0?
Horizontal at 0.
Horizontal at 0, that's actually the x-axis. This is the same as y equals 0 right here. This guy is y equals 0. I should have, as I mentioned last time, made my axes not so solid. Because this one is not part of the graph. It was just there for reference. That's my y-axis. I'm not making my x-axis dashed because that was one of my lines. That was y equals 0. Can you see the enclosed region? How would you describe that shape? You have to put it in words. I don't know. What's it look like to you?
Skateboard ramp.
What'd you say?
Skateboard ramp.
Ooh, a skateboard ramp. I like that. That's the best one I've ever heard. You guys see a skateboard ramp? I'm not getting on it. It's awfully steep looking to me. And it's really a quick turnaround. I guess it depends on how big it is, right? We need some perspective. We agree that's the enclosed area. Looks like a skateboard ramp. So the direction said to draw that region, draw a representative rectangle, which I'm going to do in a minute, and find the volume of the solid obtained by rotating the region about the specified line, and it says about the x-axis. Here's where the 3 dimensions comes in. About the x-axis. So we're going to take that beautiful picture. Now here's where you have to use your imagination. We're going to take this green polka dotted shape and rotate it out of the board, around, all the way back through until it comes back to where it started to get a three-dimensional shape. What the heck is that going to look like when we do that?
What do they call those things where you pour a shot of alcohol into each side? Looks like one of those.
Ooh, I don't know what those are called. A thing where you pour alcohol into both sides?
It's like a jigger or something.
Oh, like a jigger. I know what you're talking about now, yes. So it's kind of going to end up, if I rotate it, it's going to be kind of shaped like this, but it's three-dimensional. I can't draw three-dimensional. Your hands go up and back down.
I was gonna say yo-yo.
Ooh, yeah, kind of like a yo-yo that's flat on the side. That's a really good one too. You guys kind of see the yo-yo? It's three-dimensional. I like that. Yo-yo. I think it's called a jigger. You're right. I haven't heard that word in years. Jigger. We'll check that. We'll have to Google that later. See if that's right. Now it's three-dimensional. You guys see that's three-dimensional? I can't draw it three-dimensional. You have to use your imagination. I also kind of think of it as like a spool of thread. You put thread on the spool, a spool of thread. So the whole goal is to find the volume of that thing. We were feeling pretty good with the rectangular solid and the cylinder, and now we've got this weird shaped thing is the problem. Everyone agree that you can't necessarily just look at it and tell what the volume is? It's not like, it's what's the base times the height, right? Why does the base times height not even work here? I heard two answers. Who was I heard someone over here. Was that you?
I said there's some curve.
Yeah, because of the curve. Like, where's the base? I mean, there's a circle on the edge over here, right? Because we rotated it around. But this circle over here is a heck of a lot bigger than this circle in here. Yes?
There's a radius.
There's a radius, but it changes.
Yeah.
That's the problem. Yeah.
Radius is equal.
Right. So if we did a little circle over here, there's some radius right here, and this edge right here of the yo-yo would have been a circle. But in here, that's an R. In here, there'd be a different radius. You'd have a different circle. See the problem? So we can't just do the area of the base times the height. Enter calculus. That's why we need calculus. The cool thing is calculus is going to let us figure that out just using the area of the base times the height plus some integration. So what I'm going to do is draw the representative rectangle that it asked for, just like we would if we were finding areas. So if I had asked you last time to find the area of this, would you have drawn the rectangle vertical or horizontal? Like the top minus bottom or the right minus left? Which way would you draw it?
Top minus bottom.
Yeah, maybe vertical, top minus bottom. Maybe something like right here. That would have been a representative rectangle. If you were finding area, we're not going to, but if we wanted area, it would have been the top minus the bottom for that one, right? So we're going to take that representative rectangle and just rotate that guy. Let's go back to the direction. The direction says sketch it, draw the rectangle, there it is, and find the volume of the solid by rotating. So imagine that I take this rectangle and rotate that out and around. I have a visual for that. I'm able to shop at the party store. I have these cool gifts. So here's a rectangle. We can forget the little curve at the top, right? Here's a rectangle. You agree it's a rectangle? So if I take this rectangle right here, it's a little bit taller right now, and I bring it out and around and rotate it all the way out through the board and all the way around to the back till it's back up there, I actually get, I know it's a fan in this case, oops, I dropped it. I actually get a three-dimensional solid. Then I get a circle, it's this way, right? I get a circle that way, and it has a little bit of a thickness, right, if it was solid. You guys agree with that? So it's three-dimensional. It's a circle that has a little bit of height. What's the area of that? Or excuse me, the volume of that? Base times the height, and the base is a circle. Right? So if the base is a circle, I end up with what we call, I'll get rid of this, let me erase this picture over here. I end up with what we call a disk. I'm going to try to draw it sideways and then I'll turn it. It ends up with like this little circle this way with a little bit of thickness to it. Right? Kind of a little slice going that way when I take it out and around. I like to turn it and make it this way though, because then to me it looks like a cylinder. It's really the same shape. It has a little bit of a thickness, and it has some radius R, some radius R, and a little bit of thickness. They call it a disk. What's the volume of the disk again? Base times height, but the base is a circle, pi r squared h. Yeah? What is the h? What is the height? I'm calling it height, even though it's sideways here. This is the height. I turn it sideways now, it is a height, right? It's the change in x, he says. Remember we talked about how thick this rectangle was last time, and we called this a dx? Dx is the height of that cylinder. So this right here, this little distance right here, that's a little dx, a little small change in x. That's how thick this is right here, or how thick this is right here. The thickness or the height of this cylinder is a dx. So far so good? What's the only thing I don't know then? I've got an expression for dx.
The radius.
The radius. I need to know the radius. And where I take this slice, I'm going to have a different radius. So right here, imagine if this was the same height as this. My radius is right here, and I get a certain size. But like over on the edge, this actually matches up with this thing. It's a bigger circle over here than it is over here. So every time I move, when I'm taking these slices, the radius keeps changing. But the radius is the distance from here up to this function. Wherever I am. So maybe I'm right here at x equals, I don't know, like a third. Roughly a third right here. It looks like x equals a third. So the radius right here would be this distance. So I would plug 1/3 into here to figure out what that radius is. And when I get all the way over to the edge, when x equals 1, I would plug 1 in there and figure out what the radius is. But we're going to do an infinite number of them, so I don't have enough time to plug them all in to find all those radii. So in general, for any x, wherever you draw it, the radius is just that y value. The radius is the distance to the function that's the radius, this distance right here. We're going to put that expression into our formula. So the volume is the area of the base, which we said was pi r squared, times the dx. Okay. Pi times the radius squared times dx. Let me underline some things here. We talked about this about already. The height is the dx. Right? The height was the dx. What's the radius? It's the y value.
X squared plus 1.
X squared plus 1. It's actually the function. X squared plus 1 is the function. That's whatever x you tell me, x squared plus 1 is going to be the answer for how tall that is. So you actually put the function in there for your radius. And that's just for one slice. And this means I want to add up all the slices. And since this is a dx, starting from where and ending at where? Negative 1 to 1. A lot going on there. A lot going on there. Let's go back to the directions again. Sketch the region. Did that. Draw the representative rectangle. Did that. Find the volume of the solid obtained by rotating it about the specified line. So we rotated it about that x-axis, and in doing so, that's what gave us this circle right here, this pi r squared. And the r is the distance from the x-axis up to your function. And then there's our little height. So now all we have to do is evaluate that to find the actual volume. Somebody asked me a question. Before your head explodes. Yes, ma'am.
If the bottom line wasn't the x-axis and it was another curve, would we have done what we did last class where we subtracted the two equations from each other?
That's a really good segue for what's coming up in a couple minutes. So right now, because this is solid, when we rotate it around, there's no hole in it, it's going to be just like this. We call this the disk method, because when we take the slice and it's sitting on the axis and we rotate it, it's totally solid when we do that. In a few minutes, it won't be touching and you'll have something slightly different, so hold that thought. Other questions? Can we evaluate that? Yes? I got one yes, and one mm-hmm. I heard a mm-hmm and a yes. In the interest of time, I'm not going to do the whole thing, but let's talk about what we would do to get started. Same thing that we were doing last time. If you wanted to get started with here. Yeah, distribute the exponent. It actually doesn't distribute it. We actually would have to multiply that out. So, and this is a constant. So I would probably take the pi out front. Just worry about that later. Multiply this out using FOIL if you need to do FOIL. So this would actually end up being x to the 4th plus 2x squared plus 1 dx. Simplifying using our algebra skills that we all remember, or will eventually, because you can't forget them in calculus. You okay with that? Multiply that out if you need to. And then we'd have to actually, this tells me to do the integration. I mean, remember, it means find the antiderivative, it means integrate. So my next step would be to make that x to the 5th over 5. And then 2/3 x cubed. Exponent's going up by 1, dividing by that new exponent. Remember all that from your previous life? Before you met me? What's the integral of 1? Just x. And then we have to evaluate that from -1 to 1. And I dropped my pi, I see, so I put it back in there. My pi is still out there. This is a little bit of busy work from here, and I'm more concerned with setting up these new things, so I'm going to leave it from here and keep going. On an exam, there are times when I just ask you to set them up, like I did on today's quiz, and there are times when I actually ask you to evaluate it, because sometimes it just gets to be a little bit too much busy work. Doing okay with that one? Questions? Ask me questions. I don't know you're lost if you don't tell me. Anybody lost? Willing to admit it? Okay, we'll go with, we can't wait for the next example then. Okay, so the disk method is at the bottom of the page. The first thing that's really important for the disk method, especially because we're getting more methods coming up, is that it says that the representative rectangle has to be perpendicular to the axis of revolution. So we were rotating about the x-axis, and our rectangle is perpendicular to that. Right here, this is perpendicular, right? That's the part they're talking about. So it all depends on where you're rotating. If you're rotating the other way, you would have to draw the rectangle another way. So you want to make sure it's perpendicular to that. For a vertical rectangle, that's the one we just did, we want to fill in the formula here. It says for a vertical rectangle U, there's a space there for you to write out what we're going to do. So for a vertical rectangle, it's going to be volume equals the integral of pi r squared dx. Why is it dx for vertical?
Because it's on the x-axis.
Yeah, because it's on the x-axis. This is a small change. The thickness is on that x-axis. What do you think is going to, so that's for a vertical. What do you think is going to happen when it's horizontal? It's going to be a dy. So this is for vertical. And for horizontal, right underneath there, it's going to be a dy. And we're going to do one of those coming up so you can see it. I left off my bounds here because we don't really know what they are. We could put an a and a b, I suppose. It all depends on what they are. To me, it's more important that you understand the big picture than you memorize the formulas. Because if you're memorizing the formula, that means you don't totally understand where it came from. If you understand that it's just the circle times the height, then you don't have to memorize it. As opposed to, was it this dy to dy? So if you're finding yourself trying to memorize, then come talk to me in my office hour in the lab and let's talk through some of it so it feels a little bit more comfortable. Okay, so let's do another example. Over on page 8, example B. Example B. On page 8. We have y equals x cubed, y equals 1, y equals 8, x equals 0, and we're rotating about the y-axis. I'm going to draw my axes in another color so they don't get in my way this time. So here's a really light sketch of my x and y axis. I recommend drawing them really faint, even when you're doing your notes or when you're doing your homework, like with pencil really light, and then putting the actual curves in darker, because what happens is your brain wants to make those part of the curves, and it may or may not be part of it. So what does y equals x cubed look like? Anybody remember that one?
It's an upside down parabola, or half of it, and half of the right side of parabola.
Isn't it?
It's kind of like that, but it's actually not part of a parabola. But you're right, he's describing the shape. It's kind of a backwards S shape, I suppose, too. He's calling that half a parabola, which I kind of agree with, but it's technically not because of the cube. But it's the right shape, though, I get you. So it's like kind of half a parabola here, kind of half a parabola here. They're not really parabolas because of the cube. But you've seen the x cubed function before. So there's y equals x cubed. Y equals 1. That's y equals 1, so let's say 1 is here. That's just a horizontal line. Y equals 8 is up here somewhere. That's another horizontal line. And where's x equals 0?
The vertical on the origin.
Perfect. The vertical at the origin, the vertical x-axis. This is x equals 0. Everywhere on this line is x equals 0. So we have y equals 1, y equals 8, x equals 0, and this was y equals x cubed. So this is my little enclosed region here. And we're rotating it about the y-axis. So we're going to take this weird shape, rotate it out around the board, over to here, and all the way through the backside and come back around. What's that one going to look like?
It's gonna be like a dome,
Couldn't hear you.
like an upside down dome.
Ooh, kind of like an upside down dome. It's a little bit bigger on the top, right? And then it kind of curves down, and then it's a little bit flat on the bottom. Kind of like that. I am not an artist. You've already learned that today multiple times. See, it's going to be something like that when I rotate it, and it's solid. The flat part comes from up here. It helps sometimes if you try to visualize. This might mess the graph up for you, so you may not want to copy this down. It helps me to try to draw a mirror image of this. So if I draw it over here as a mirror image, it looks something like that. And then I kind of just picture that, and I put a little circle here, then I can kind of see what it's doing. But for some people, it's hard to visualize, so it really depends on how you can draw it so you can see it. That's how I got that shape over there. And I'm going to erase this card. Okay. So which way should I draw my rectangle?
Perpendicular to that.
Perpendicular to the axis. So since we're rotating around this axis, we want it perpendicular. So we need a little rectangle going this way. Because it has to be perpendicular to that axis that we're rotating. I like to think of it as just do it the same way as if you were trying to find the area. The right minus left kind of situation that we were doing. You okay there? Can you see that it's a dy now? This little thickness of this little strip right here, this rectangle is thick, a small change in the y direction, that's why it's a dy. So my volume, remember, is pi r squared dy in this case. What's the radius in this case?
X cubed.
X cubed? Mm-hmm. No?
No, it's cube root of 1.
So he's technically right, and you guys are on the right track who said x cubed. It is the distance over to that function. I completely agree that this distance to that function is r, right? Because that's what you're going to rotate around. That's your radius. But this distance, is this an x or a y value when you're moving left to right? That's an x value. So we need to know what that function is. We have to solve it for x, just like we did last time. Because remember, that's a dy right here. Everything I put in there better be in terms of y. I can't put x cubed in there. So it needs to be in terms of y. So this distance, this radius, is an x distance. Meaning it's moving left to right. Like this is a distance on the x-axis down here, right? That's how far it is. Some arbitrary x. Like maybe right here, x might be, I don't know, a half or something. So we have to solve this equation for x. We're going to take this guy over here, solve it for x, take the cube root of both sides. X equals the cube root of y. So just like before when we were doing areas, if you have to turn everything in terms of y's, turn everything in terms of y's. This dy right here tells me I need to have everything in terms of y. But the distance is just the distance to the function. Everyone all right why I did that? So what's my radius in this case?
This one is the cube root of y.
The cube root of y. So I'm going to have pi times the cube root of y squared. Right, that's my radius. Times dy. What are my bounds?
1 to 8.
1 to 8, she says? Because we're starting at y equals 1, going all the way up to y equals 8. We're going to slice it at 1 and keep slicing these all the way up till we get to 8. And this is how I'm going to find the volume. I'll get 2 here in a second. Can't stress enough that I want you to ask me questions. If you're going, why did she write cube root of y there? Or why is there a squared there? Or why is there a dy? I need you to ask me. Because you got to do it on your own later. So you might as well ask me now before you're frustrated on your own. Anybody have a question? You think we understand it? We're hoping it sinks in later. You guys are quiet, makes me nervous. Think we're good? Why the cube root of y? Does that make sense? Like let's where I drew this rectangle, I'm going to guess that looks to be like y equals 5 right here. 5 question mark? Looks like I'm about 5 on my y-axis right there. If I'm at 5 and I wanted you to find the radius right there, if y equals 5, you'd plug 5 in here and have to solve for x to figure out what that distance is, right? And to solve for x, you would take the cube root of 5. That's where that comes from. Okay, you guys make me nervous without any questions. I'm going to go with you guys are all with me, but I don't believe it. That's why I'm nervous. Okay, let's talk about how we would do this one, because some of us forgot our algebra. We didn't forget it. It just got a little rusty over the very long break. If you wanted to get started on evaluating this, besides taking the pi out front, what would you do to integrate that?
Argument 1/3.
Beautiful. Change that cube root into an exponent. That's a y to the 1/3. Remember, a cube root is a 1/3, a fifth root is a 1/5. So the first thing I would do is I would take the pi out front, and I would do exactly, is it Daniel? What Daniel said, and change that to a y to the 1/3. And be able to interchange between roots and exponents like you did back in algebra. And then what? I don't usually pause for algebra, but it's the beginning of the semester. I'm being extra nice today.
Would it be y 2/3?
Yes. So you multiply those exponents, that's one of the rules of exponents. Y to the 2/3. So that's pi integral from 1 to 8, I'm running out of room here. Y to the 2/3 dy. And then we could integrate. And to integrate, what would we have to do first? I heard somebody say something, I didn't hear what it was. Come on, who was that? Go ahead.
Find the antiderivative.
Yeah, how? What would you do to find the antiderivative?
You put the exponent on the in the denominator and subtract one.
You're close. You're thinking of a derivative. So we want to add one first. So we want to find the antiderivative. You're going to first add one to the exponent. So the exponent is 2/3. So it's going to be 5/3. And then I have to divide by that 5/3. I'm going to move up here so you can see it back there in the back of the room. The pi is still out there. I'm going to now have y to the 5/3, because I added 1 to 2/3. Fractions happen in life, you just have to accept it. Just because you don't like them doesn't mean you don't do them. There's lots of things in life that fall into that category. Laundry is one of those. I don't like doing laundry, but I do it all the time. It's kind of like fractions. And then I want to divide by 5/3, which is a shortcut of doing that is to multiply by 3/5, yes. 3/5. And then we still would have to evaluate it from 1 to 8. Good? I'm going to finish this one because it'll let me algebra reminds it a little bit more. The pi and the 3/5 are all just constants. I'm going to leave that all out front. That's all constants. And basically I'm going to end up with 8 to the 5/3 minus 1 to the 5/3. Right, because the constants you can distribute now or later. I like to leave them until later. Saves me some space. And here's where a lot of you want to grab your calculators. I claim you don't need to. You don't need to. If you just pause for a moment and jog your little memory, you'll be okay, I swear.
Do we still need dy?
Good question. Once you find the integral or you find the antiderivative, this integral sign and the dy, they come off simultaneously. So these two together, this piece and this piece, tell you to integrate. And once you integrate, the dy is gone and the integral sign is gone. So at this point, this just says now you're just evaluating this. There's no more calculus really to be done besides just plugging those numbers in. The dy is always gone after that.
Apply the cube root first.
So this goes back. So just like Daniel knew to change the cube root into a 1/3 exponent, now we're going to change it back into a cube root so it's easy to evaluate. This right here, 8 to the 5/3, which looks scary, just means find the cube root of 8 and then raise it to the 5th power. That's all that means. You learned that in algebra, you just don't want to remember it. Cube root of 8 to the 5th power. So I'm going to write this as 3/5 pi because it looks prettier to me. What's the cube root of 8?
2.
So that's 2 to the 5th. What's the cube root of 1? 1 to the 5th. So I have 3/5 times pi. 2 to the 5th is 32. 1 to the 5th is 1. I'm running out of room here. I better finish this problem up. 3/5 pi times 31. See if I can squeeze the answer in there. I'll put it right here. This is going to be so beautiful in the video. 93 pi over 5. You laughing at my arrows? Laughing at the answer. It's a beautiful answer. It doesn't have a square root of 7 in it. It could be worse. Questions? That was kind of a longer one. I took some time to do some of the algebra. I have to warn you, I'm not always going to do that. Pretty soon you got to know your algebra. You just have to write yourself a little note. The setting it up part is the hard part. That's the part I'm most worried about. So let's go back to Lila's question though about what if there's a whole What if it's not on the axis? This one was on the x-axis and we rotated about the x-axis, and that one was on the y-axis. What'd you say? They could be overlapping, but I actually won't give you one of those because those are pretty messy. But the idea is that your region maybe doesn't touch the axis. Maybe something like, maybe your region is up here. You know, here's my region up here. And if I'm rotating it about the x-axis, when I rotate it, it's not going to touch it. There's going to be a hole. Like it'll be hollow on the inside. That's more what we're talking about. Because if it overlapped itself, then that's kind of a little bit weird. They could, but that's more than I'm going to ask you to do. The extra credit, baby. In the middle of the page 8 there, right underneath that example we just did, in general, we're finding the area of the base times the thickness. And we already talked about that. Now, what if it's not on the axis, which is where that next picture came from, right? It's a little bit different than that. So the only thing that's different is when I rotate it, it's going to be hollow in the middle, right? It's going to have this hole in the middle. So what I like to think of is, I like to think of rotating this outside line all the way around, which makes it solid. And then I kind of think of, then do the inside one and cut that part out. So you're doing the outside one minus the inside one. Just like the areas we're doing, the top minus the bottom. So we're taking the outside volume minus the inside volume when it doesn't touch there, when it's hollow. And we will always have two radii. So let me draw that picture in a better place so we can see it. I'll draw it over here. So imagine I'm going to redraw that same one that's on bottom of page 8 there. What time is it? Time for our break here? Not quite. Let me just draw this little bit and then we'll take the break while you think about it, and then we'll do some more of those after the break. So I'm talking about the picture on the bottom of page 8 that looks like this. Roughly like this and like this. And we have this representative rectangle here, already drawn in there. And we're going to rotate it about the x-axis. So when I go to rotate this thing out and around the x-axis, it comes all the way down here. You guys all see it's not going to touch it? It's going to have a hole in the middle. I can't use this as an example anymore because this rotates right around here. I need it to rotate down here, but then there's nothing there. There's like this gap right there. So if I rotate this out and around, remember again I talked about drawing a mirror image on the other side? Here's my little mirror image of that slice. That's pretty close. About the same distance on the other side. This part gets rotated around, and this part gets rotated around. I'm such an artist. You kind of see that? Yes, sir.
So then would we try to find the area between the two and then subtract that?
Well, you can't start with the area between the two because you actually have to find the volume between the two. Yeah, so you have to find the volume and subtract. You can't just do the area. Like you can't just right. So you can't just subtract the y value. That's the important thing. We can't subtract the y values because the y values are the radii, which gets squared. But you are going to do like the outside volume minus the inside volume.
Yeah.
You guys all see that this little shape, I'm going to draw it sideways. Once I rotate it, it's going to look something like this, with some thickness to it, of course, because I'm such an artist. Beautiful. Use your imagination. It's going to look something like that. We call that a washer because it has a hole in the middle of it. And so if you wanted to find the volume of this, we take the bigger circle and find the volume of that little disc and minus the disc that we cut out in the middle here. And we will always talk about the outer radius and the inner radius, which is on the bottom of that page. The bottom of that page says note. The outer radius is the distance from the axis of revolution to the outer curve. So this big radius here, I'm going to draw it sideways here. This is the big radius, capital R. The outside curve, right? That's capital R. And then inside here, to the inner curve, that'd be little r. Right? In a bigger circle, smaller circle. R1 and R2, I like these capital and lowercase. The lowercase is lost in there, don't I see it? Oh, I stepped away. Little r. Well, we could do R1 and R2. That's fine. Where on this picture are the r's? Capital R and little r. this distance here, he says, Chad, right?
Yes.
Chad, yeah. Chad says this is the capital R, so the furthest distance is your big radius, and this inside one here is your little radius. See the two different circles you get there? One from the top one, and they come from the two functions. So to find the volume, guess what we're going to do? Subtract the two. We're going to take pi times big R squared. In this case, is a dx or a dy? Dx, right? Because I have a change in the x direction. Minus pi times the little r squared dx.
They have the same bounds.
Yes, they have the same bounds because they're both going to go, say, from A to B. So they have the same bound, they've got the same dx, the same pi. You can actually put these together nicely as, let me write it higher so you guys in the back can see it, as pi times the integral from A to B. Oh, that doesn't erase, it's stuck down there. Times what? What goes here? Big R squared minus little r squared. 2. It's getting worse as I try to fix it. They call this the washer method. It's really not different than the first one, it's just because there's a hole in it. If there's a hole in it, you have to subtract off that inner part. We're going to do an example of this after our break. Questions? Okay, let's take a good 10-minute break from there. Come back, we'll finish this, do a couple more. See how much more we can cram into our brains. Well, those of you who hadn't bought your notes yet and came in at a disadvantage, but I gave you the notes, I figured out what the problem was. Nobody spoke up. By the way, speak up, people. I am not psychic. If you're confused, the pages are missing and it's only every other page. So you went from the first page, which ended with the disk method, and then the next page said example 2. So the first page was really page 7, and the next one you have is page 9. You're missing page 8. So everything we just talked about, you don't have. It's going to happen again after the next page. So you have only every other page, which is better than nothing. Buy the notes next time because I'm not bringing any of them. So that's what happened, is you lost every other page. But if ever your notes and my notes don't match, just interrupt me, guys. I don't know that they don't match. Okay, well now we're going to pick up with example 2, which you all have. Page 9, example 2. Again, sketch the region, lots of drawing here. Sketch the region, draw a rectangle, and find the volume after we rotate. So example 2. Example 2. We have x equals y squared, y equals 1/3 x, and we're going to rotate about the y-axis. So we got two functions, we're rotating about the y-axis. Hopefully we can draw those. What's x equals y squared again? Parabola that opens sideways, right?
Yep.
So x equals y squared. There's an x here, isn't there? 1/3
Yep.
x. Here's x equals y squared. Rough sketch of that. Y equals 1/3 x. That's the graph of a line through the origin. Has a slope of 1/3. So maybe it looks something like this. It's just a rough sketch of it. Where's the region enclosed by those?
Finish the parabola?
Yeah, I need to finish that parabola. I need to make it come over here and touch that line, something like that. So there's my little region in here. And we're rotating this about the y-axis. So we're rotating here around the y-axis this way. So this piece is going to come out and around. I even want to try to estimate what that's going to look like. Don't give me a word for that one, because I don't know what it is. Some of you could probably get creative enough. I couldn't do it. Which way do I want to take the slice? Vertical or horizontal? Horizontal, because it has to be perpendicular, right? So this is where we're rotating. So perpendicular to that, I need a little slice this way. Always perpendicular to where you're rotating. You see the issue now, how it doesn't touch the axis? There's a gap right here. That's what tells you it's going to be a washer instead of a disc. Imagine that you're going to take this piece and rotate it. I like to draw a little circle here. And then you're going to take this piece and rotate it. You guys could probably almost see that one. Almost. I think he's not even. He's just humoring me, right? So you have two circles there. The outer radius is the distance to this big circle. The inner radius is this one here. Yeah, right there. So the volume in this case is going to be, I'm taking the pi out front here, and I'm going to take r squared, big R squared minus little r squared dy. Because there's a small change in the y direction here. So big R squared is the distance from the origin out to this function. This is big R, all the way out to there. And this little guy in here is little r. It's a little tiny r in there. What do I need to do with my functions to set this up?
You gotta equal the two equations.
Say that again?
Equal the two.
Oh, set the two equations
Yeah.
equal. I need to set them equal because that's going to give me what? The bounds. I need the bounds. I don't know where I'm starting. I think I'm starting at 0 from my picture, but I'm not so sure what that is. So I need the bounds. But what else do I have to do to be able to plug them in here? Change them so they're in terms of y. So that means I have to solve for x in each case. Instead of y as a function of x, we have x as a function of y. This one's already good. This is already x equals a function. But this one I need to solve it for x. So I'm going to come up right here, solve for x, multiply both sides by 3. You get x equals 3y. Yeah?
Yeah.
So I'm going to find the bounds here in a minute. By solving those for x, I can at least write out what this part looks like. What is capital R? 3y, the distance to this function, which is the line, and the line is 3y. So capital R, let me write it right here. Capital R is that function, and little r is the distance to this function, which is the parabola, which is y squared. So I'm going to have 3y squared minus, I forgot what it was already, y squared squared dy. Okay, guys, I make it look easy because it's easy for me. If it's not easy for you, please ask. Because you should be sitting here thinking, hey, I have to do my homework later. Well, I'm not sure why she wrote that. I need to figure out why. And then ask me. Raise your hand, interrupt, I don't care. I want to help you figure it out. You okay with that? This is my common feedback I get. Like, it makes so much sense when you do it, Jill. But then I get home and I can't do it. That's why you got to ask me a question. Ask yourself, what part of it am I not so sure about? No questions? Okay, now I need to find the bounds. I'm going to take her suggestion and set these equal to each other so I can find what those bounds are. So I want y squared to equal 3y. This function to equal that function. It's a quadratic, so I'll set it equal to 0 to solve it. We did some practice on this last time. Factoring's a really nice technique here. Y equals 0 and y equals 3. So we already knew that one was 0 right here. This one right here, where it tops up here, this is y equals 3. Where it touches up there at the top. 0 up to 3. So we're going to start slicing at 0 and keep taking those slices till we get to 3. Yes?
If we had set the functions equal to each other, but in terms of x, would it still work?
Yes, I love that question. So her question was, what if she had done it in terms of x and set them equal to each other? So maybe you would solve this one over here and you would have had y equals square root of x, right? And then y equals 1/3 x. So if you had set those equal to each other, I'm not going to do the whole thing, and you had solved this, you would have ended up with x equals 9. So her question was, would we get the same thing? And I said yes. And some of you are going, that's not the same thing.
You plug
But it
that
is.
in.
Go ahead.
If you plug that in.
If you plug that in, this is an x value. When x equals 9, if I'm over here and x equals 9, plug it into either equation. If x equals 9, y must have been 3. Right? So sometimes you're not sure if you're doing a dx or a dy, and there's some that you could do both ways. So you might need to solve for x, you might need to solve for y. If you solve for the wrong one, you can switch and figure out the other one just by plugging them in. Because this point right here is the point 9, 3. Turns out in this problem we don't care what the x is, but there's another time where we might. I'm glad you asked that. So then what are my bounds here?
0 to 3?
0 to 3, because we're doing the y values. dy tells me. So remember yesterday, by the way, when I say yesterday, I mean last time we met. And when I say tomorrow, I mean next time we meet. Every day. It's all yesterday and tomorrow. Otherwise I have to correct myself every time. I've told you how important it is to write the dx or the dy, and some of you said, we talked about how you forget to write them. It's crucial here, because if you don't write the dx or dy, you might put the wrong variables in there and it messes everything up. Changes your bound, changes your calculations. Make sure you have those, it means something. And this goes back, actually, Daniel was asking about the quiz you started when it says set up the integral. This is what I mean by set up an integral. Just at least write the integral that represents what we're trying to find. You don't need to evaluate it, it would be to take the busy work to multiply it all out and all that, but this would be setting it up. Obviously, to answer the question, we keep going. Questions on that one? You think we're good? Here's what I want you to do. By the way, the washing method's in the middle of that page 9 that we're looking at now. It pretty much says the same thing we're doing. Take the volume and take the area times dx. It doesn't really make a lot of sense. But what I want you, and the volume is the big volume minus the little volume, so it really doesn't really say anything on there. I want you to read number 3 and try to draw the picture and draw where you're rotating and look and see how it's different than what we were doing. So everyone should have example 3 down at the bottom of page 9 if your pages are numbered. That starts with y equals square root of x, x equals 4. I want you to try to draw that picture and think about what it would look like. The radii will be different in this case. We'll go through that together, but I want you to draw the picture on your own. See what you get. Most of us have the picture, some of us are trying to set it up. Let's draw the picture here. I'm going to try to draw my giant if I can, so that if I can make my point better. So y equals square root of x is this. X equals 4, oops, it doesn't go back down. X equals 4 is this. And y equals 0 is here. So we end up with this slice right here. I mean this region right here. Most of you had that, no problem? Ooh, I almost tripped. But it though, I haven't thought about it. Where are we rotating?
About x equals 4.
About x equals 4. So we're rotating about this guy. So we're rotating about that. So a lot of you were taking my advice and you were drawing, you know, the mirror image over here to kind of see what it would look like after you rotated it. Do you want to draw that? So you're going to end up rotating it out and around to get that same thing. We were talking about the slice, the rectangle, perpendicular to the rotation, or the axis of rotation. We call this the axis of revolution. If I need something perpendicular to this guy, my rectangle has to be sideways, horizontal, correct? Here is my rectangle that is perpendicular to where I'm rotating. So it's not perpendicular to one of the lines that you drew, it's perpendicular to whichever line you're rotating around. You're always rotating about some line. So my question for you is, where on this picture is the radius? Bless you.
Thank you.
It's allergic to calculus. It's all bad. So many weeks of this now. Where's the radius? Yes, ma'am.
Is it from x equals 4 to y equals square root of x?
Yeah, it's this distance from here to here, right? Because you're going to rotate this to get my disk. This right here is going to be my radius. Because we're going to rotate just that guy around right here and get this little disk right here. When we rotate it, we see that this distance is our radius. It's no longer just the function though. It's not just a function. It's the distance between here and here. It's r. We could just call it r, life would be easier. So here's what I like to do. This point right here is just some arbitrary point that I just picked to where I was drawing my slice. This distance right here is just some arbitrary x value.
4 minus r.
Yes. Do you agree that's just some arbitrary x value?
Yeah.
And here's the radius that I'm looking for. Can you tell me how x and r are related to each other? In any way? Like maybe the distance from here to here?
X plus y equals 4?
X plus r equals 4. You agree with that? X plus r equals 4?
Yeah.
This distance plus that distance is 4? Solve for r. R equals 4 minus x. So I have an expression for my radius, 4 minus x. Maybe that's good enough. We'll find out here in a minute. Is this problem going to be a dx or a dy problem? dy? Why is it dy? Yeah, because this is horizontal. The thickness here is a small change in the y direction. So when I go to set up my integral here, I know I need pi r squared dy. Put it a little higher so I'm consistent. Pi r squared dy. Okay with why it's a dy? Which means whatever I plug in there, better have y's in it. Oops. We were doing so well until then. This has an x in it. But this x is just a distance to this function. What is this function? It's the equation, this guy right here. This is y equals square root of x. So this same equation is x equals what?
Y squared.
Y squared. That's an error I just pointed out today. This same equation is the same as we're saying x equals y squared.
Yeah.
So this x is just a function. So when I said r was 4 minus x, now I'm going to rewrite it as 4 minus y squared. Why do I need to do that? I know why. I want to know that you know why. Are you thinking?
Yeah.
Thinking's good. Who wants to try to tell me why I had to do that? How did I know I needed to change from 4 minus x to 4 minus y squared?
Because we have dy.
Aha, because we're going to integrate with respect to y. And if I'm going to integrate with respect to y, whatever I put in there better only have y's in it. So sometimes you have to switch things, sometimes you don't. There's not a hard and fast rule, it all depends on which way you're setting up the problem. If this problem had been given to us like this, we would have already had that x was y squared, and it would have been easier. All depends on how it's given to you. So to set the volume up for this problem, I'm going to pull the pi out front. Oh, another question before I go any further. How did I know there was only one r instead of two?
Because there was no hole.
Oh, there's no hole. How can I tell there's no hole? What makes there no hole?
Because there's only one function.
Oh, that's not always the case. Sometimes there might only be one case and there still could be a hole depending on where you're rotating. If I was rotating about like the y-axis, there would have been a hole.
Because if you put it into a three-dimensional figure, it's not gonna have.
Yeah, but how, so I guess my question is, how can you tell from the two-dimensional figure that when you make it three-dimensional, there won't be a hole there? It's connected to this axis of revolution. So because I'm rotating about this axis and it's touching this axis everywhere, because it's touching it, that's what tells me it's going to be solid. If it's not touching it everywhere, that's what makes the difference. Okay, so we took the pi out front. The radius we agreed was 4 minus y squared, and we still have to square that radius. The radius squared, right? Pi's out front, the radius is squared. dy. Uh-oh, what else do I need?
The limits,
I need the limits, the bounds, yes.
from 0 to 2.
0 to 2, he says. Do we agree with him? Where do you get the 2?
The value
There's
of
no
x.
2 here anyway, I don't get any 2's.
The value of x is given as 4.
Uh-huh.
Plug it into the square root.
We were told that x was 4 right there. X is 4 right here, so we know right here that this point is 4 comma something. Right? 4 something, and the something is the one that comes from this graph, which is y is the square root of x, so y is the square root of 4. So this has to be 2. You will always be using the functions they gave you to figure out whatever points you need. If we had been doing a dx problem, we wouldn't have cared about that 2. But because it's a dy problem, we had to figure out what that y value was. Because you're finding out there's multiple pieces to these problems. And sometimes they have everything in the right place all lined up, and sometimes you have to do some algebra and some rearranging and add in a few more things. I'm not going to evaluate this one either. But that's going to be how we're going to find the volume for this particular solid. The big difference with this one is because we're not rotating about the axis, the radius could be weird. The radius is definitely harder when you're not rotating on an x or a y axis. In this case, it was 4 minus x. I like to do exactly what I did on this picture. Draw the x, draw the r, and figure out that relationship. It makes coming up with this a little bit easier. A lot of people will guess, is it x minus 4? Is it 4 minus x? Which one is it? Or I think with this picture, most of us can see that x plus r equals 4, and then go from there. Other questions about this one before we do one more ugly one? Yes, ma'am.
So when I first tried to set this up, I set my radius equal to y squared and not 4 minus y squared. And if I'd done that, would my radius have just been like from the y-axis to the function?
Yeah, so when you said the radius was y squared, that's this distance right here. You were saying that this little piece, I don't want to write it on here, who read it? You were saying that this little piece right here was r, like rotating that.
Okay.
See why that wouldn't work there? And that's almost, I mean, that's kind of the, goes, let me erase this before I forget. That goes back to what I was saying earlier about don't try to memorize the formulas, because if you memorize the formulas, depending on where you're rotating, it might just be the y squared, but if you're rotating somewhere else, it's different. And the more you can understand the subtleties of how the pieces are related, the easier it gets in terms of being a little more straightforward on why one piece works or doesn't. Because it's too hard to just tell you this is always the formula, because we keep moving where we're rotating it. But I'm glad you asked that. Everyone see what she was asking? Because that would be most people's assumptions. Like, oh, let's make it y squared. It's that function. I like to always label my r in there as well in my picture. Other questions before we try the next harder one? We're going to run out of hard ones today. That's good. Okay, so those of you who had my handouts from earlier don't have this next one. Oh wait, is it down here at the bottom? Not this. So you don't have this next one. It's the same region, rotated about a different line. So it's the same region. So this is example 3b. Example 3b, same region, but now we're rotating about y equals -1. So I'm going to redraw the region and draw my -1 in there. So the region hasn't changed. It's still the same region here. Still have this point up here, 4, 2, might as well put it in there while we're at it. And we're rotating that about y equals -1, which is down here. Here's y equals -1. Okay, I just drew the same region and put that -1 in there. Is my rectangle, is it horizontal or vertical?
Vertical.
Vertical this time, because it has to be perpendicular to that guy. Vertical. Here's my little rectangle that is perpendicular to this one. And I'm rotating it about this thing. Not this one, but this one. Is there going to be a hole in it?
Yeah.
Yeah, because it's not touching this line at all. So when I rotate it around there, it's going to be totally hollow in the middle there, right? When I rotate it, again, I sometimes like to draw this little mirror image down here of my rectangle. To see that I'm doing this and that. See my washer? My little mirror image down here? I missed the edge, sorry. Here we go. Did I do it big enough? I want to label my big R and my little r. The big R is the distance from wherever you're rotating, the middle, all the way out to that edge. So this right here is my big R. From wherever I'm rotating all the way to the edge of that circle. And little r is from wherever I'm rotating to the middle of the little circle. So this little guy here would be little r. That's a really horrible picture. I did it from the wrong side. Let me fix it. Little r. You see the big R and little r? Dx or dy? Dx, dy, who I heard about controversy.
Or do you?
Dx? Hesitating.
Yes.
Why?
The width of the rectangle.
The width of this rectangle is a small change in the x direction, right? A small change on the x-axis. So that's what makes it a dx. So it's a dx. I'm going to go ahead and put my pi out front right from the get-go. I leave room for it. And I know I need big R squared minus little r squared. So I need an expression for both of my r's. R equals and little r equals. One of them's easy, I think. Or easier, maybe. I think little r is kind of straightforward. What's little r? 1, right? Just 1? This distance here is 1. No matter where I draw that slice, that little r is just from here to here, that distance is always just 1. That one's easy. 1. the big R? Big R is a little bit trickier.
What's the square root of x?
Yes, I like it. So you're a step ahead of me. So this big R, I wish I had like 14 other colors. I thought I really switched it here. I'll be able to see it. Maybe I'll stick with the blue. Is this distance plus this distance, right? That's big R. It's the solid blue line plus this dashed blue line. The dashed blue line right here is 1. What's this distance right here?
Square root of x.
Square root of x, it's the function, that's what he was saying. This is just the function. Again, like I did on that other one, I'm just going to call it y for the moment. This is some y value. Similar to how I said that was some x value over here, right? That's just some arbitrary y value. But in this case, because it's dx, it's actually, where's my function? Since y equals square root of x, that is this y value right here. So the big R is whatever that y value is plus 1, but we have to convert it into x's. It's this y value plus another 1. And this y value is just some square root of x. I swear your brain's really not going to explode. It only feels like it. It's good for you. Keeps you young. Alzheimer's will take that much longer to set in. We'll all be good. Pi times the integral. Big R is this expression, right? Square root of x plus 1, the quantity squared, minus 1 squared dx. Everything here is in terms of x, so I'm good. Didn't have to change my function in this problem. It already was in the right format. What are my bounds? 0 to 4. Because these are the x values now. X starts over here at 0 and goes all the way until I get to 4. Remember this point we talked about earlier? It all depends on if you're doing dy's or dx's. In this case, it's 0 to 4. Again, it makes sense when I'm stepping you through it and explaining the why. This is so fun, isn't it? All right, so here's what I want you to do. Some of you don't have this example, so I'll put it on here. I want you to try to set up the next example and see why what we've been doing today won't work. It's kind of a little segue into what we're doing next time. I'll write it up here for those of you who don't have it. So this is example 4. Everything we just learned was great. We think we might finally get it, and now Jill tells me it won't work. I want you to draw the picture and see if we can talk about why it doesn't work. So example 4 has a little bit messier quadratic here. Might take you a little while to graph that one. And y equals 0, and we're rotating about the y-axis. So I want you to sketch that region, draw the representative rectangle, and try to articulate why we have a problem. A little clear on the directions? Okay, let's see if you can get that. Almost there. Looks good. Okay. So your graph, you ended up with something that ended up looking like this for your region. There's some more to the graph. You should have had this for your region over here. Yes? And we were rotating about, this was the function y equals 2x squared minus x cubed. There was more to it, but this was the part that was enclosed because it was enclosed by this axis and that. And we're rotating it about the y-axis. So to do that, I need to draw my slice horizontal, because it has to be perpendicular to the axis. So here's my little slice. Okay, here's my slice horizontal. If I'm rotating it about this axis, I'm going to have my inner circle here, and my outer circle there. You guys are starting to like my art, I can tell. Okay, I see it now. So, little r is this distance. This distance right here is little r, the inner radius. And big R is way over here, distance to that outer edge. So little r touches what function? This one. And big R touches the same function. Oh, I said, it's like mind blown. What the heck? If it touches, I mean, it can't have the same function minus itself because I'll get 0. Right? If I take this one squared minus this one squared, I'll get 0. Right? Because they're the same function. So the big problem here, when it says at the bottom of your notes, it says, what's the issue here? Both radii touch the same function. So I can't say I want 2x minus x cubed squared minus 2x minus x cubed squared, because it all goes away. You guys see that problem there now? So this is an example of one that you cannot do with the washer method or the disk method. Disk would only be solid. What we're going to do next Tuesday is learn yet another way to find these that does work. So we can't finish this problem today. We're stuck. Okay, so let me give you a couple announcements and reminders. Reminder is that on Tuesday, next time I see you, you are going to turn in 6-1 lab and your 6-2 lab.